So, we will discuss a few more problems. So, problem number 12 is the partition function of a system represented by q equals to exponential of a t to the 3 times v, where a is a constant, calculate average pressure, average energy to the 2 and heat capacity at constant volume. Problem number 12 is the partition function of a system represented by q equals to exponential of a t to the 3 times v, where t and v are absolute temperature and volume respectively, and a is a constant. And we need to calculate average pressure, average energy to the 2 and heat capacity at constant volume, at constant heat capacity at constant volume, or CV. It's a pretty straightforward problem. So, partition function is given and we know average pressure is kBT del ln q by del V at constant number of particles and temperature. So, this is the expression for average pressure. So, we need to take log first. So, ln q gives us a t to the 3 times V and del ln q by del V, constant number of particles and temperature, gives us a t to the 3. So, average pressure is kB times T times A T to the 3. So, it gives us kB times A T to the 4. So, this is the expression for average pressure. Next, we need to calculate average energy to the 2. So, average energy is kB T to the 2 del ln q by del T at constant number of particles and volume. So, del ln q by del T at constant n and v, we get 3 a t to the 2 times v. So, average energy we are getting 3 a kb t to the 4 times v. So, once we get the average energy, we can calculate average energy to the 2, which is nothing but 9 a to the 2 kb to the 2 t to the 8 times v, v to the 2. Okay. And then we can calculate CV. So, CV is del u by del T at constant volume. So, we get CV is 12 A kb T to the 3 times V. So, as I said, this is pretty much straightforward problem. Only thing we have to apply the equations. We have to do the differentiation with respect to V. We have to do the differentiation of ln Q with respect to V and with respect to T in order to get average pressure and average energy. Once we get the average energy, we can calculate the average energy to the 2 and CV from there. Okay. So, next problem is very interesting one. It says, suppose one mole of an argon gas molecular weight is 40, argon gas are first held rigidly in position and then allowed to move freely. What is the change in entropy? You can consider temperature is 298 Kelvin and pressure P equals to 1 atmosphere. So, this problem says, suppose 1 mole of an argon gas or argon atoms are first held rigidly in position and then allowed to move freely. What is the change in entropy? So, the catch here is the molecules or the atoms, they are rigidly held in their positions and then allowed them to move freely. So, if they are held rigidly in their positions, means initial entropy is 0, since the argon atoms are first held rigidly in their positions so S initial is 0 and we need to calculate entropy change, means entropy change we say delta S for the process is S final minus S initial, and we have obtained S initial 0. So, we need to calculate S final. So, for S final we have to apply Sackur-Tetrode equation. For calculating S final, we need to apply Sackur-Tetrode equation. So, what is Sackur-Tetrode equation that we already derived? Sackur-Tetrode equation is S, or he in this case is final, is we have 1 mole of argon gas. So, Na times Kb, then logarithm of twice pi m kbt by h to the 2 to the 3 by 2 v e to the 5 by 2 and by Na. So, 1 mole means Na here, Kb value we know 1.38 times 10 to the minus 23 in joule unit, and mass of argon here. So, mass of argon, m is mass of argon. So, mass of one argon atom is 40 by Avogadro number times 10 to the minus 3 kg. And we need to know the value of volume. Okay. So, how do we get? So, because if we considering ideal gas, temperature and pressures are given. Considering ideal gas, we can write V is nRT by P, N is 1, R is 0.082 in liter atmosphere unit, times temperature is 298 and pressure is 1. So, this is in liter. So, we get V in some value of liter. From there, we need to calculate volume in some value of meter to the 3. We have to convert it. Okay. So, if we substitute this, we get delta S here. Okay. So, we get the value of delta S is 155 joule per Kelvin. Okay, if we substitute all these values. So, the catch here is we need to consider that initial temperature is 0, because all the argon atoms are fixed, they are not moving, and we need to calculate S final. For calculating S final, we need to use Sackur-Tetrode equation. So, Sackur-Tetrode equation says S final is number of particles times Kb, and then ln twice pi mass times Kb times temperature by h to the 2 and whole to the 3 by 2 volume e to the 5 by 2 and divided by number of particles. So, the unknown quantities in this expression are m, mass of argon atom, we can calculate from the molecular weight of argon atom, and it is said that 1 mole of argon gas is there. So, N is nothing but Na in this case, and then we need to calculate volume. For calculating volume, we consider ideal gas equation of state, and then we consider N at V equals to nRT by P. N is 1, R is 0.082 in liter atmosphere unit, and temperature is 298 K and pressure is 1 atmospheric pressure. So, if we substitute all these things, we get volume in liter. Once we get the volume in liter, we need to convert volume in meter to the 3. Okay. And once we get the volume, we substitute volume, mass and number of particles in Sackur-Tetrode equation to calculate S final. Once we get S final, we can calculate delta S, which is nothing but S final, because as S initial is 0. Okay. And if we substitute all these things, we get delta S, or change in entropy is 155 joule per Kelvin. So, again this is a straightforward problem, but you need to think before start solving this problem. Next, we consider another problem, problem number 14. This is a very simple but again interesting problem. Consider Na number of Na equals to Avogadro numbers. Na is nothing but Avogadro's number. So, consider Avogadro's number of distinguishable particles. Distinguishable and identical particles. Each of which can be placed into 3 available energy states having energies zero epsilon, which is the epsilon is doubly degenerate, and 2 epsilon respectively. Where epsilon is 300 times k beta. By considering canonical ensemble, calculate Helmholtz free energy A in joule unit at a temperature of 'So, problem number 814 is consider Avogadro number of distinguishable and identical particles, each of the particles can be placed into 3 available energy states having energies 0 epsilon, which is epsilon is doubly degenerate, and 2 epsilon. So, it says that 0 and 2 epsilon states are non-degenerate, where epsilon is the value of epsilon is 300 times Kb, 300 times Boltzmann constant. By considering canonical ensemble, calculate Helmholtz free energy in joule unit at a temperature of 300 Kelvin. So, all particles are identical as well as distinguishable. So, molecular partition function Q is sum over I Gi times e to the minus beta epsilon I, where Gi is the degeneracy of the ith state and epsilon I is the energy of the ith state. Here we have 3 available states, so I goes from 1 to 3. So, if we expand it, we get Q is G1 e to the minus beta epsilon 1 plus G2 times e to the minus beta epsilon 2 plus G3 times e to the minus beta epsilon 3, and G1 is 1, G2 is 2, G3 is again 1, and epsilon 1 is 0, epsilon 2 is epsilon, and epsilon 3 is 2 epsilon, as mentioned in the problem. So, we will substitute this. So, we get Q is 1 plus 2 e to the minus beta epsilon plus e to the minus 2 beta epsilon. So, it gives us q is 1 plus e to the minus beta epsilon to the 2. So, this is the partition function or partition function of a single particle. Now, we can further simplify q. So, q is 1 plus e to the minus epsilon by kBt to the 2, and the value of epsilon is given 300 times kb. So, if we substitute that, we get 1 plus e to the minus 300 times kb by kb, and temperature is given 300 to the 2. So, the value of q is 1 plus e to the minus 1 to the 2. So, this is the value of partition function, molecular partition function of a single molecule. So, we have got a number of identical as well as distinguishable particles. So, since particles are distinguishable, so canonical partition function of any number of particles if we say canonical partition function is q is function of nVt is q to the na. Here n is nothing but na. So, we get q, canonical partition function q is 1 plus e to the minus 1 whole to the 2 na. So, this is the partition function of the system having n number of identical distinguishable particles. So, once we get q, we can calculate A. Okay. So, A is minus kBt ln q, minus kBt ln q. So, we need to calculate ln q. So, once we get q, we get ln q is twice na ln 1 plus e to the minus 1. So, we get A is minus kb times t times twice na ln 1 plus e to the minus 1, and na times kb gives r, gas constant r. So, minus 2 RT ln 1 plus e to the minus 1. And if we further simplify that, we get minus 1563 joules, okay, joules per mole. Okay. So, this is the value of Helmholtz free energy at 300 Kelvin temperature. Okay. So, next we discuss another simple problem. Consider a system that can be in one of two states having energies zero and twice epsilon respectively. Considering both the states are equally likely calculate the average energy epsilon and the variance of energy sigma epsilon to the 2 in thermal equilibrium at temperature T Kelvin. So, this the 15 problem is consider a system that can be in one of two states having energies 0 and 2 epsilon respectively. Considering both the states are equally likely, calculate the average energy epsilon average and the variance of energy sigma epsilon to the 2 in thermal equilibrium at temperature T Kelvin. So, it is given epsilon 1 is 0, epsilon 2 is 2 epsilon, and there is nothing mentioned about degeneracy. So, we will consider these are non-degenerate states. So, and the both the states, since both the states are equally likely, so P1, so probability P1 equals to half and P2 equals to half, where P1 is the probability of state epsilon 1 and P2 is the probability of state epsilon 2. Okay, so we need to calculate average energy. So, epsilon average is sum over I goes from 1 to 2 because only two states are available, Pi epsilon 1. So, this is the definition of average of any average quantity. So, epsilon average is P1 times epsilon 1 plus P2 times epsilon 2, and if we substitute the value of P1 is half, epsilon 1 is 0, and value of P2 is again half, and epsilon 2 is 2 epsilon. So, we get average of energy is epsilon. And next we need to calculate variance of energy or sigma epsilon to the 2. So, variance of energy epsilon is epsilon to the 2 average minus epsilon average to the 2. Now, epsilon to the 2 average, because epsilon average we have already got. So, epsilon 2 average is P1 epsilon 1 average to the 2 plus P2 epsilon average to the 2. So, we get epsilon square average is half times 4 epsilon to the 2, or we get 2 epsilon to the 2. So, variance of energy epsilon is 2 epsilon to the 2 minus epsilon to the 2. So, we get variance in energy sigma epsilon to the 2 is nothing but epsilon square. So, again this is a very straightforward and simple problem. Okay. The next problem we discuss is another analytical problem, so that if a partition function is of the form Q NVT is Q to the N by factorial N, where N is the number of particles, V is the volume and T is the absolute temperature. And if QVT is function of T times volume, then the ideal gas equation of states results. Here V is volume and T is absolute temperature, and N is number of particles. So, this problem states so that if a partition function is of the form Q is molecular partition function to the N by factorial N, and if molecular partition function is of the form function of T times V, then the ideal gas equation of state results. Okay. And here also I should mention Ft is function of temperature only, a function of temperature only. So, we need to obtain ideal gas equation of state, and Q is given here. So, we need to calculate pressure or average pressure. Okay. So, Q is Q to the N by factorial N, and Q is given as function of T times volume to the N by factorial N. So, in order to calculate pressure, we need to calculate first logarithm of partition function. Once we get the logarithm of partition function Q, we will differentiate the partition function with respect to, we will differentiate logarithm of Q with respect to volume at constant number of particles and temperature, we get the average pressure. So, as I said, so we need to calculate logarithm of Q. So, logarithm of Q is N ln function of T plus N ln volume minus ln n factorial. So, del ln Q by del V at constant number of particles and temperature. So, first term gives 0, second term gives N by V, and third term is again 0, and average pressure is nothing but Kb times T del ln Q by del V at constant number of particles and temperature. So, if we get the value of del ln Q by del V as N by V, so if we substitute, we get N kBT by V, and N kBT is nothing but, N kB is nothing but N times Na times Kb times T by V. So, we get average pressure times volume is N at T, where capital N is nothing but N times Na, Na is the Avogadro's number. and small n is the number of moles. Small n is the number of moles and Na is the Avogadro's number. So, we have proved that average pressure times volume gives nRT. So, I repeat again. So, here molecular partition is a function of temperature times volume, and the partition function of the system Q is Q to the n by small n, or molecular partition function to the n by small n factorial. Now, if we substitute molecular partition function by function of temperature times volume, then if we take the log of that, we get ln q equals to n ln function of temperature plus n ln v minus ln n factorial, and we need to obtain, or we need to get the ideal gas equation of state. So, in order to get the ideal gas equation of state from the canonical partition function, we need to differentiate ln q with respect to volume, because this gives us pressure. If we multiply d ln q or del ln q by del v with by kb times t. So, we get, if we differentiate, we get del ln q by del v is capital N by V, or capital N by volume, and then pressure is kBt del ln q by del V at constant number of particles and temperature. So, if we substitute del ln q by del V by N by V, we get N kBt by V, and then we get N pressure times volume gives nRT, or small nRT, where small n is the number of moles and Na here is number of Avogadro's number. And then the next problem is another analytical problem. Calculate the equation of state associated with the partition function Q, and V beta is 1 by factorial n twice by m by h cross times beta to the 3n by 2 times v minus nb to the n, then e to the beta a n square by v. Where A and B are constants and h cross is h by twice pi, beta is 1 by kBt. V is volume, n is number of particles, and T is absolute temperature. So, this problem says calculate the equation of state associated with the partition function Q, which is 1 by n factorial times twice pi m by h cross to the 2 times beta to the 3 by n by 2 times v minus nb to the 2 and e to the beta an to the 2 by v, where a and b are constants and h cross is h by 2 by twice pi, 2 times pi, beta is 1 by kBt, and v is volume, n is number of particles, and T is absolute temperature. So, this problem is very similar to the previous problem we just discussed. Again, we need to calculate gasification of state from the partition function. So, we need to calculate average pressure from the partition function given in the problem. So, partition function given in the problem is 1 by n factorial So, in order to get the pressure from the partition function, we need to first get logarithm of the canonical partition function q, and then we need to differentiate with respect to v, and then the product we get, if we multiply by kBt, we get the average pressure. So, q is given here. So, we need to now calculate logarithm of q. So, ln q is minus ln n factorial, and then minus plus 3n by 2 ln twice pi m plus 3n by 2, not my plus, minus 3n by 2 ln h cross to the 2 minus 3n by 2 ln beta plus n ln v minus nb, and then plus beta an to the 2 by v. So, average pressure is kBt times del ln q by del v at constant number of particles and temperatures, or beta. So, we get kBt, and del ln q by del v, if we differentiate ln q with respect to v, the first term gives 0, second term 0, third term again 0, fourth term 0, fifth term gives us n by v minus nb, and the sixth term or last term gives us minus beta a n to the 2 by v to the 2. So, we get average pressure P is n kBt by v minus b minus a n to the 2 by v to the 2, or we get average pressure plus a n to the 2 by v to the 2 times v minus b. This gives us n kBt. So, again I repeat here. So, this is nothing but this problem is based on. So, so at the end we get van der Waals gas equation of state. So, again I repeat, this problem, in this problem partition function is given as 1 by factorial n times twice pi m by h cross to the 2 times beta, and whole thing to the 3n by 2, then v minus nb to the n and e to the beta a n to the 2 by v, where a and beta are constants and h cross is, we know h cross is nothing but h by 2 pi, where h is Planck's constant, beta is 1 by kBt, where kb is Boltzmann's constant, and v is volume and n is number of particles and T is absolute temperature. So, from this partition function, we need to calculate the gas equation of state. So, we know from the previous problem that in order to get gas equation of state from the partition function or canonical partition function, we need to calculate average pressure. So, from partition function expression Q, we first get logarithm of Q, and then we differentiate the logarithm of Q with respect to volume, and then the resulting thing, if we multiply by Boltzmann's constant time temperature, then we get the average pressure, and then at the end we get average pressure is N times KBT, KB times T by V minus NB, not B, V minus NB here. Okay, so NB here. Okay, so we get V minus NKBT by V minus NB, and then we have minus A n to the 2 by V to the 2. So, if we rearrange, we get P plus A n to the to the 2 by V to the 2 times V minus NB equals to N KBT, which is nothing but Van der Waals gas equation of state. Thank you.